Um, so the talk I'm going to give is about quantum natural language processing, as we call it, for near. So NISQ devices is an acronym that is thrown around a lot in quantum computing lately, and basically it means noisy intermediate scale quantum. So it's the devices we have today, and I'm going to talk about what we can do with such devices for NLP, or what we think we can do. So I want to recognize support from the Royal Commission for the exhibition of 1851, which is a very nice fellowship that I was very lucky to have, and it's based in Oxford. And also I'm advising for Cambridge Quantum Computing with a company in Cambridge, and they also they have to be credited for starting this field of QNLP and supporting us to do research in this topic. So let's begin. So this talk is about how we go from word to sentence, and then to diagrams, and from diagrams to quantum circuits, and from quantum circuits to NISQ devices, these noisy devices that we have today, the quantum processors. So what I'm doing here is I'm completing Joachim Lambeck's book title, and I claim that I'm taking it a step further, and I'm building on his mathematical model for grammar called pre-group grammars, which I will introduce later. And also I'm building on Bob Cookes and his collaborators' disco-cut model. So that's a distributional compositional categorical model of natural language meaning. And that's the diagram part. And the contribution of this talk, which is the asterisk, is how we go from these diagrams to NISQ devices. So this is what I said in words, but now it's shown as a pipeline, which we introduced in this preprint here, which was accepted to QPL, a conference in quantum physics and logic, recently in June. So basically the pipeline is as follows. So we start with a sentence in a corpus. A corpus is just a selection of a big set of sentences in our case. Then these sentences, we convert them to diagrams according to the grammatical model of pregroups that I will introduce later. To these diagrams, we do some manipulations here, and we get new diagrams out. This is kind of a detail here, but it's necessary, as we will see. And then the most important part, which makes these things quantum, is the use of quantum machine learning in this arrow, where we use parameterized quantum circuits as Ansatz to encode the semantics of these diagrams that represent grammatical parsings of sentences. Then, once the meanings are encoded in Hilbert spaces, and Hilbert spaces are basically the space, they are the spaces in which quantum states are defined, it's where they live. So after that, what we do to send circuits, quantum circuits, which are abstract templates for how to prepare a quantum state, you actually need to send it to a device. And this is done through a compiler or a simple transpiler. So the job of the compiler is basically to take the abstract circuit or program in machine language, in quotes, or quantum machine language, and send it to an actual device. So for example, this would be a quantum device by IBM, or some ion trap device, like for example by IonQ. And let's start this whole pipeline with an example. I think if we follow this example, it will be very clear what we're doing. So we can take the sentence bugs, trolls, poor Elmer. So first of all, I won't deal with questions of ambiguity that are asked a lot. For example, bugs could be the plural of a bug, but I won't deal with this here. However, there are proposals in this framework that I will use that attempt to deal with ambiguity, for example, by the use of density matrices in quantum theory, which basically are probability distributions over pure quantum states. But for anyone who understood what I said, That's fine. For anyone who didn't, that's also fine. This is not the point of this talk. So let's take bugs, trolls, poor Elmer. So a parser would come here as a first in the first step of the pipeline, and the parser would assign these types. So these types are what we call pre-group types, and they are types that are assigned to parts of speech. For example, bugs is a noun, Elmer is a noun, trolls is a transitive verb, poor is an adjective, and these types are a product. In general, they are a product. For example, the verb type is a product of 3 types, and I have N, which is the noun type, to the R. R means right inverse, and L means left inverse. So this is like, it's like in standard algebra where we have an inverse of an operation. So for example, if we have natural numbers and A is a natural number, the inverse would be to the -1. And I could write it like this, and I would get 1 because A to the -1 is the inverse of A. Here I have 2 inverses. So it really matters on which side I'm multiplying from. So for example, A to the R multiplied from the right, multiplying from the right A, and A to the left multiplying from left A, both give identity. So this is all you need to remember here. There are some types called pre-group types. They are assigned to part of speech accordingly. And a sentence is grammatical when only the S type survives after all the other types annihilate to identities. So for example, this N and this N to the R annihilate to the identity which we don't draw. And the annihilation process is depicted by this line. So you can imagine that 2 things go in here and nothing comes out. And the nothing is the identity type, which I'm not drawing. It's the empty diagram. So this is how this is the first step of passing from a sentence to a diagram. So also I want to say, I want to encourage people to ask questions and interrupt me at any point here if things are not clear. So I want to ask, is everything clear so far, how the parsing part works?
Yeah, this is Seth. If you have questions, you should use the Q&A feature, or you can also use the chat. And by the way, the presentation will be recorded and posted to our YouTube channel, and I will post the address after the meetup.
Okay.
I don't see any questions so far.
Okay, I'm just going to continue then. Thank you. So that was the first step of, oh, I see a question. So after the reduction shown, is the result that only S survives? Yes, yes, indeed. So you see, there is only one dangling wire, this one. And this means that only S survives because all the other ones are paired up so that they annihilate each other because they're all inverses of each other. And only S survives. It flows downwards here. So only S surviving is the witness of grammaticality. So for any sentence for which this is possible, we call it a grammatical sentence in this grammar model. Also, on what basis N and N to the R or R to the L are assigned to these words? So this is done just by with a classical method. It's I should give a reference to Preller. So the reference is linear processing with pregroups by Preller. This is
You're typing something that's not visible. Oh, I'm sorry. I'm sorry. It is visible. Yes.
Yes, I wrote it on the slide. So this is the title of the paper that describes the parsing, which can be done efficiently with this pre-group grammar. How can you be 100% sure that Elmer is a noun, not say adverb or preposition? Okay, yes. These are good questions, but since for now we are considering the parsing to be the first initial step, and we consider it solved. And what we do later is take these diagrams and try to compute their semantics, as I will say later. And this computation will be done with a quantum device. But we assume that the parsing step is already solved for us because it's an efficient problem, and we actually there is a student in Oxford that works with us who is working on building this parser in Python. And of course, a next step for future is to combine the semantics with the parsing part, but for now we're keeping them separately. Okay, so let's continue. So that was how the diagram of the parsing of the grammatical parsing of a sentence looks like. And then the DiscoCat model introduced by Bob here and the two other authors, Mernouche and Stephen Clark. So this is the sentence, this is the reference for the DiscoCat model where it was first introduced. So the idea here is that words are assigned vectors or tensors, and the parsing, the grammatical parsing, tells you how to contract these tensors. So in high level intuitive explanation, I would say that word meaning states go into the grammar, which is the piping through which the meanings flow, and then the sentence meaning as a whole is combined from the meanings of the individual words according to the grammar. This is the idea here, and this is how it looks with the diagram. So before I had this diagram. So these cups here, or these wires that connect the words, they can be seen as a vector, as tensor contractions. And these triangles, these boxes with triangular roofs, they can be seen as vectors or tensors. So a vector is a triangle with one leg. A tensor is a triangle with 3 legs or more legs. If it has 2 legs, we call it a matrix, right? This is standard linear algebra. So the idea here is that every word gets a tensor, and after the grammar, after a tensor contraction, which is done according to how the grammar tells you, you prepare a vector, right? Because this whole thing is a big vector because it has only one leg sticking out. So this is the sentence meaning vector. This is how DiscoCat works. And the first in the first works of DiscoCat, of this DiscoCat model, they fill these tensors with co-occurrence vectors and tensors in a bag of words style encoding of the distributional meanings of the words. So we have a question: can these methods be realized using tensor networks in classical computers too? Yes, they can. However, because these D's here and these D's, these are dimensions. So they are the dimensions of the vector spaces flowing through the wires, right? And of course, they are type dependent. So here, before I had an N, and here I had an N to the R. So along this wire, I have a dn space. I have a dn dimensional space, and I treat it as a hyperparameter of the model. So in practical applications, this can be very big if you're doing bag of words encoding. And I mean, as far as I know, this can get really big. So you have to do some dimensionality reduction tricks and so on to be able to contract these tensors without having memory overflowing problems. But yeah, the answer is yes. Okay, so here, let me recap a bit on the notation I'm using. So for example, I've been using triangles that have legs sticking downwards as states, and I will be calling the states upside down as effects. And if you, so this is process theory diagrammatic language, but it's useful to actually set my notation straight so that things are not confusing. So always imagine that time is flowing downwards. So this is a state that has no inputs, has the empty diagram as an input. Something is prepared here, and we have a vector flowing out. So this we call a state. The effect is the dual of this. So we have a vector space flowing in, something happens, and nothing flows out. So it's an effect. If you put a state and an effect together, we have a scalar, so a number. And where this number belongs, in what field, it depends on your vector space. So for example, if you have real tensors, then it's a real number. If you have complex, then it's a complex number in general. I see we have a question. Can you please give a very simple example of how to generate the co-occurrence vector mathematical wise, even after you finish, please? Yes, I can discuss about the co-occurrence at the end, if you don't mind. I didn't mention co-occurrence vectors in detail here because they're not the point, because we're going to go quantum later. And basically, I just mentioned it because they were heavily used in the beginnings of this disco-cut model. But since this talk is about going to quantum circuits instead of doing tensor contractions on classical circuits, I can say something about it in the end if there is time. Putting a lot of states together, we call it a product state. If you put them like this side by side together, you have to imagine that there's a tensor product between these vectors. So this is what we call also in quantum theory a product state or a classical state. In general, a many-body state will be, as you would intuitively expect, a big triangle with nothing coming in and a lot of wires coming out. So this would be a state, a collective state, a many-body state of as many bodies or qubits or systems in general in process theory, as many wires as we have here. So, or a tensor if you're doing it classically, okay? So I have two special states here, this cup and this cup. So this is a special state, or if it's a quantum theory, we call it a maximally entangled state. And this is a maximally entangled effect. And they satisfy the snake equation, which means that the wires can wiggle, basically. That's what it means. And we're going to use that. So putting for example, a cup and a cup together, you can yank it and get the identity wire. Okay, let's go. So the first QNLP paper was by Will and Bob. And basically, what they want to say with this paper is that language is quantum native, as Bob repeats. So take this sentence. This is its sentence, this meaning vector. But you have to imagine that what was done in this paper was to take these things, these vector spaces, to be Hilbert spaces. So this is how you go quantum. You imagine that these are quantum states, and so this is a quantum state on 3 qubits, for example, if a wire carries a qubit. This is a state on 1 qubit, and so on. And the grammar applies maximally entangled effects on all the qubits except 1 qubit line, which survives. And that's how you prepare the sentence as a quantum state. This is done at a high level. So for example, ds would be of this dimension, where ns is the number of qubits that you allocate to that wire or to that space. The same for the n. And the same if you have more types. I'm just using a very simple example here where I'm using only s and n types. But the pre-group grammar can get very complicated. You can have many types, and for each one you can have a dimension assigned, or like a number of qubits that you allocate to that, and then you can play with it. So in this paper, they argue that you can get a Grover-style speedup, a quadratic speedup with a quantum computer, if you search over closest vectors when you compare two sentences together and see how close they are with a cosine distance. I can show you diagrammatically what this looks like in the end. We call this sentence similarity or phrase similarity. But I'm just citing this here as the first paper that thought, oh, what if we use quantum states, and what if we make these D spaces to be Hilbert spaces, these dimensions to be exponential in some qubits? And what the motivation here is that, as we said before, because the D's can get really big, these dimensions practically. For example, they were considering co-occurrence vectors. Well, if they get really big, then maybe you can encode them in a small number of qubits, in a logarithmic number of qubits, because the Hilbert spaces, when you put n qubits together, grow exponentially. So a Hilbert space, you can see it here. I mean, for n qubits, the dimension is 2 to the n. So they wanted to take advantage of this to encode high dimensional spaces to a small number of qubits. And there was a reshaping that was needed to retain the speed up. So for example, for any sentence, what you need to do is reshape the diagrams. And I told you that you can always reshape the diagrams because the wires are bendy, right? So you can wiggle them around. So if you wiggle this sentence through this wire, what you're doing is you're creating a bipartite graph where you're converting some of the states to effects. So an effect is a word rotated 180. So, for example, this noun Ross was turned 180 and was converted to an effect. So this was stated in the original Zeng-Coecke paper, but these guys here, Stefano and Nicolo from Hashberg, who are also co-authors on the first paper of the pipeline that I cited in the first slide, and this talk is about. What they did is they generalized this to arbitrary sentences because Zeng and Coecke did not produce code for it. So you will soon be able to find code on how you can parse and also reshape these sentences to these bipartite graphs that are basically as thin as possible. Thin as in, if this is the width of the sentence, this is what they're trying to minimize by introducing these swaps and turning some states to effects. So another type of reshaping that you might want to do was done by Alexis and Giovanni, who are in our who are both PhD students in Oxford and also part of our Cambridge quantum computing team for quantum natural language processing. And what they did is they used the result from Antonin, who has this paper where basically he autonomizes monoidal categories for anyone that has any idea what these words mean. But in diagrams, what this means is that you can take a state like this, like draws, which is made of 3 types, right? It has 3 wires because it has 3 types, and some of the types have adjoints. Adjoints are these inverses, so to the R and to the L. So what you can do is you can replace the state by this box, and a box is a process. It has some inputs. This is how you write a generic process, and some outputs. So this is a process. Draws becomes a process with 2 inputs and 1 output. And you replace them so that the adjoints are now flowing. They become inputs, and you supplement these cups here, these maximally entangled states, so that you can bend them around. And basically, what you've done is you've replaced this state with this process with 2 inputs and 1 output. And now that you've done this, you have these snakes. And using another paper by Jamie Vickery that we're citing in our paper, you can yank the wires and get something like this. So this can be done automatically after one is given a parsed sentence. And you can find code that does this in Python in this DiscoPy repo. And also there is an accompanying paper on this on this library, which is very extensive, and I think there's enough information for anyone interested to go and play around. And also, Alex and Giovanni used it in the context of language game, where they try to formulate basically to use DiscoCut in the context of Wittgenstein's language games. So these are the tools that we're going to use. And okay, this is just a quick recap slide, and maybe I should pause here for questions. So as I said, there's a pre-group parser that assigns types. Grammar gives me the skeleton. The meat on the skeleton is given with vector spaces in the form of effects and states and effects. In particular, if you want to go quantum, states are quantum states, effects are quantum measurements, and maximally entangled ones to be specific. And then I'm going to continue and talk about parameterized quantum circuits, which is our contribution. How is a snake defined? The GitHub is not available. Yes, indeed, the first GitHub is not available. The DiscoPy should be available. The first GitHub by Hashberg should be available soon. Stefano is working on that. How is a snake defined? So a snake is nothing much. So for example, take the snake like this and cut it in 3 pieces. So you see here, I have a maximally entangled state going in, tensor producted with an identity. So an identity is just nothing, is the identity process that leaves the input invariant. Here I have 3 identity wires flowing downwards, tensored together. And here I have the identity here, tensored, a maximally entangled effect. And this should be the same as the identity. You can do this with tensor contraction and verify that if you have this tensor, this tensor, this tensor, this tensor, and this tensor, and this tensor, and this tensor, and you do these operations where horizontal composition is the usual Kronecker product, the tensor product, and vertical composition is matrix multiplication, then you will see that this is satisfied. In general, okay, I have to say, okay, if you want to do this yourself, what you're really using is this tensor. Let's take this dot tensor, and this one has 3 legs. So let's call it leg 1, leg 2, leg 3. This tensor has these entries. It has a 1 if L1 equals L2 equals L3, and 0 otherwise. And a maximally entangled state is basically this tensor with no inputs and 2 outputs. So basically it's a column which has a 1, 0, 0, 1. The effect is that thing, but transposed. And the identity is just the identity matrix. So the wire flowing downwards is just the 1, 1, 0, 0 matrix. And if you compose these things with tensor product, and if you horizontally, and if you compose them vertically with matrix multiplication, you will see that you will get back the identity. It's just very easy to. Okay, can you recommend some basic books on some of these concepts for those who are new in this area? Yes, of course. So there's a very nice book by Bob, the famous Dodo book. So Bob, Coecke, and Alex Kissinger. It's called Picturing Quantum Processes. It's a purple book with a dodo on it. It's very comprehensive. It starts from scratch and introduces this diagrammatic notation from scratch, and it will be, yeah, for anyone interested in diagrammatic quantum calculus, it's a very good introduction. another question. Okay, let's continue. Okay, so recap. We see what we did, right? We have the grammar telling us how to combine the tensors, or if it's quantum, it's telling us between which states to apply quantum effects, maximal entangled ones, vectors. The states are quantum states, and then the question is what is in the states, right? So let me remind that any state is basically a process, right? I said before, a process is a box and it has some number of wires as input and some number of wires as output. So a state can be always prepared. This is preparing a state from a trivial state. And I'm symbolizing the trivial state by this tensor product of a bunch of lollipops. And the lollipop is in quantum computing the zero state. So it's if you go to IBM's quantum experience and you try to make a circuit, every circuit will be a bunch of gates, quantum gates or boxes or processes acting on some tensor product of zeros. It's the reference state for most classical algorithms. For example, this is the 0, 0 state and so on, right? So from the all zero state, there is a parameterized by this set of thetas process that prepares the state of a word. I see we have a question. Does this snake tensor's probability amplitude S encode any meaning? No, the snakes only encode the grammatical parsing. So the cups are there only according to the grammar. And if a word has ambiguity so for example, a sentence can have ambiguous parsings. It can have one or the other parsings, and it would be grammatical in either case. So that means that there is not only one way to put cups or these maximally entangled effects on words, on triangles basically, so that only the S type remains. It can be ambiguous. So all the meaning is in the states, right? So this is the meaning here. The meaning is in here, or the semantics as we say. And the meaning is a process that prepares the state from the reference state of all zeros. So it's a parameterized process, as I said. So if you want, for example, the state for ROS, there is a parameter set, thetas, of some size for ROS that specifies ROS. And similarly for draws and snaky and spiders and so on. So how do we build these word processes? How do we construct? What is the internal working of this box, right? So this is how we go to quantum circuits. We say, oh, let's take some families of gates, some gate sets. For example, a controlled knot and single qubit rotations. In diagrammatic form, they are these. So this is the traditional notation for the controlled knot, the C knot. This is the notation I'm using in this work, which is, it comes from the ZX calculus. This is something that you can find in the Dodo book of Bob and Alex. The ZX calculus is a fully diagrammatic, sound, complete, and universal language. It's fully diagrammatic, and it's for all of quantum theory. And basically, I'm using a mixed quantum ZX notation, but it doesn't matter. All you need to know here is that there is a family of generators. So the control knot, this one, and the same but inverse. So like this is the target, and no, this is the control, and this is the target. So for example, if the control is 0, the target is flipped. If the control is 1, sorry, if the control is 0, the target gets an identity, nothing happens to it. If the control is 1, then the target qubit is flipped. This is the same, but I've switched control and target. And this is the generic single qubit rotation. So these are the three Euler angles, alpha, beta, gamma, that can hit a qubit and rotate it around the Bloch sphere. So this is the Bloch sphere. The state of a qubit is a vector pointing somewhere on the surface of the sphere. And we have three angles, right? We have this angle, we have the rotation angle, and we have basically, yeah. And there is a global phase. Let's say this one. So the Bloch sphere is parameterized by three angles, and three angles define the state of a qubit. So another family we can use is this gate set. Instead of CNOT and single qubit rotations, we can use this one. So this is the Hadamard gate, which basically sends the 0 state to the plus state. And the plus state is basically the equal weight superposition of 0 and 1. It sends the 1 state to the minus state, which is the same but with a minus. So this is what the Hadamard gate does to the input qubit. So input comes in and output comes out. If the input is 0, for example, you will get the plus state out. So this is the controlled Z rotation. This is the standard way to depict it here, and this is my way to depict it. So for example, this is the control qubit. If the control is 0, nothing happens to this. If the control is 1, then this qubit is rotated around the Bloch sphere, around the z-axis of the Bloch sphere with the angle theta. Okay, so for example, here I've given you two gate sets. So this is gate set number 1, gate set number 2. In the following, I'm going to use this one, but this is also equally valid. And here I've chosen these because, for example, the IBM devices can do CNOTs natively. It's in the hardware. So it's good to build your circuits, to construct your boxes or your processes that prepare your states, to construct them in terms of the gates that are native to the device that you might want to use, right? So this is good for IBM. In general, ion traps are good to do Z rotations, controlled Z rotations, and so on. Okay. So here's an Ansatz that uses these two gates, so the Hadamard and the control Z, and I'm constructing it like this. So you start with the all zeros, right? These lollipops, as we said, are the zeros. They flow in. You hit the first layer, L1. They go through a bunch of Hadamards and they become plus states, right? And then they go through this layer of control Zs. And this layer of control Zs between every neighboring qubit has an angle. So this is a set of angles. This is the set of angles of the first layer, and so on. The second layer will have its own set of angles, and the last layer will have its own set of angles. And all of these angles are basically the classical parameters of this process. So for example, a word would be specified by setting these parameters, these thetas, these sets of thetas, to some specific values, and it would generate, this quantum circuit would generate the state that encodes the meaning of that particular word corresponding to that set of thetas. So is this clear? It seems it is. So, okay. So let's continue. Okay, there is a question. No. So what is the specific question? Maybe someone wants to unmute themselves.
Chris, who said no, I unmuted you.
Yeah, I'm not sure I have the background to understand. I'm not sure whether we're doing linguistics or physics.
Okay, so maybe the
But I think that's my issue.
okay. Let me recap what I'm doing. So what I'm doing is I'm setting up a template which is friendly to the devices we have today, that generates that so that we can generate states. We can prepare quantum states in a controlled way. The control is these parameters, these classical parameters theta. Imagine you are in your lab with some knobs and you're just turning them, setting the thetas to their values. And basically, having this setup, I'm able to generate whatever state I want to encode the meaning of the states. And then the linguistics is going to be some task of optimizing these parameters, as I will show later. But what I'm trying to say here is that this is one way to load classical linguistic data or the meanings of words as states prepared by quantum circuits, quantum states prepared by quantum circuits. So it's like,
so in essence, what we're doing is we're mapping certain basic NLP functions, linguistic functions, into a quantum world. We're looking at quantum representations of these NLP functions.
What's your definition of quantum?
The definition of quantum here is that I'm using quantum states to encode the meanings. So basically, what's my definition of quantum? My definition
I'm not
of quantum
sure.
is that anything that runs on a quantum circuit is quantum by definition.
Is an item a quantum?
Sorry? An item, did you say?
Yeah, as I said, I don't think I have the background to fully understand what you're talking about.
Okay.
And that's okay. I don't want to hold everyone up.
So the idea behind quantum is that it's capable of representing a multiplicity of possibilities simultaneously for resolution at some point. Is that fair, Konstantinos? But I do suggest we move on.
Yeah, let me give it another try in 5 seconds. Imagine that it's another way of doing tensor network contraction. So instead of having these vectors and tensors living in your classical device, you have these quantum circuits to represent state preparations and measurements of the same tensor networks. And then instead of doing your contractions on a classical device, you do them by measuring some qubits after you have prepared some states on them. So preparing the states is encoding the meanings. Measuring the qubits is basically applying the effects of grammar to it so that you prepare the state of the full sentence. It's preparing the state of the full sentence so then you can do something with it.
Can I try to paraphrase?
Yes.
Sure. So I would say, the application here is quantum means being able to represent an entire state space explosion of hypotheses. And then, as you were saying, being able to maintain all of the hypotheses simultaneously without blowing out memory, and then being able to retrospectively decide what was the most likely.
Yeah, I guess you could do that if you're doing some inference problem. From what you're saying, that's what you're that it seems that you're proposing. A similar thing is happening here. So, for example, the motivation to go quantum is that you have so much Hilbert space, which is the space of quantum states, which is exponentially growing in the number of qubits. So the motivation is I have these tensors that are very high dimensional. And what I'm trying to do is encode these high dimensional tensors in quantum circuits and taking advantage of the fact that qubits define a huge space, an exponentially big space. So I'm saving up, I'm using this huge space to encode my meanings. Imagine it's like a compression.
Yeah, okay, just being able to handle an enormous state space that we couldn't otherwise handle.
Yes, yes. Also, another motivation to go quantum, say, is the compositional structure of the pre-group grammar model. So these, it's not, this is not an accident that you have pre-group types assigned to, for example, if you go back, these types, they have a product between them. And the mathematical structure of these products and how they compose together to fuse into the identity, or if you have more complicated pre-group types, how their product structure and their compositional structure really reflects the compositional structure of quantum theory, where we have a tensor product, and vertical composition of diagrams is basically composition of circuits in series. So we have all of these maths that is agreeing in the background. And this is what Bob has as a slogan for, that language is quantum native. This is what he means by this. So, and this is how the DiscoCAT model started, because there was some lecture by Lambeck at some point, and then, or maybe Bob was giving the lecture and Lambeck was in the audience, and Bob was drawing diagrams of quantum theory, and Lambeck said, oh, but look, these are like pre-group diagrams. So what I'm trying to say is that the compositional structure is so similar that it really is inviting for this application. Okay, so let's go back. Okay, we have a comment by Mike. I think it is the meaning of meaning as you use it that is confusing here. What do we expect the meaning of ROS or draw to be? Thanks. Okay, yes, this will hopefully become clear in a bit, because I haven't really specified it. So this is where the machine learning part comes in. So here is a note. If you want to convert states to effects, you have to do 180 rotation. This is the 180 rotation of that previous diagram. It's very straightforward to do, just showing it here. Let me show you specifically what the circuit of a sentence looks like as an example, and then I will address the question by Mike. So this is the reshaped circuit of a sentence. So Ross draws snaky spiders. The hyperparameters are set here so that I'm giving 1 qubit to the sentence space, 2 qubits for each noun wire, and D, which is the depth of the IQP Ansatz, or is 2. So I have 2 layers here. I have 1 layer, 2 layers for every word. So draws has 1, 2, 3, 4, 5 legs, and it gets 10 parameters. These 10 vita, how many? 8. These 8 vitas. Ross has 2 parameters, alpha 1, alpha 2. Spiders gets 2 parameters, delta 1, delta 2, and so on. So this is the quantum circuit. Specifying for this sentence. So it prepares the meaning, the semantics of this whole sentence on this 2-dimensional single qubit wire. This is the S wire, and every wire here carries one qubit exactly. It prepares so after you specify all of these angles, alpha, beta, gamma, delta, all of these sets of angles, if you specify them, then this circuit can run on a machine, and measuring that qubit in this 2D space, you will get something out. You will get a 0 or a 1. And this will be, in our application, what the meaning is, just a binary value. But this can be generalized. Why do you select IQP ansatz? How about other ansatz? Yes, so this was just an example. As I said before, what ansatz to use really depends on the machine. So for example, for IBM's machines, you can generate your Ansatz with C-notes and single qubit rotations. So it depends on what machine you want to do. Any universal Ansatz will do. And also like from quantum chemistry and other quantum machine learning applications that are not physics-based, but are more, trying to do classical machine learning tasks with quantum computer, what they're basically doing is trying a bunch of Ansatz randomly and see which works better. Okay, so let me continue here. This was just for me to illustrate you how a circuit looks like. This is a legit circuit. It can run on a device. This is low level. I just wanted to show you something low level. This is a slide that shows 3 devices by IBM, so that you get an idea of the problems that you might run into when you want to do some implementations. For example, these are the Rochester, Paris, and Singapore devices by IBM. So this has 53 qubits, this has 27 qubits, this has 20 qubits. And you see not every qubit talks to any other qubit. They all have their own connectivity. So basically a compiler needs to come in. So what we use this Cambridge Quantum Computers compiler, which basically its job is to take a circuit like this and fit it on an architecture of a quantum device. So we use Ticket to solve this annoying problem for us. And also what you have to do is try to minimize the depth of these circuits as much as possible, because we don't have error correction in quantum computing yet. So that would be the holy grail of quantum computing. But because these devices are noisy, they can be very, very annoying. So if noise comes and kills your superpositions, makes everything classical before you're able to prepare your states and do your NLP task, then there is no point in doing this at all. So let me go to the NLP part, which is basically this loop here. So we would get a bunch of sentences in a training set. So sentences with some index I and some labels Li for every sentence. So this label for us in the implementation we did is basically a 0-1 label, a binary label. For us, it was something like true or false, for example. So every sentence, to every sentence, we get for every sentence, we construct a circuit as in exactly the way that I've been talking about up to this point in the talk, by choosing, we take its parsing, we fill the boxes with some ansatz, and we have circuits. Then we send these circuits to, let's say the IBM's device, some IBM device, and we estimate the S wire. So for example, for every sentence, we have this wire carrying a qubit, and if you measure it, you either get a 0 or a 1. And getting a 0 or a 1, you can send the 0 or a 1 back to your laptop, say, and you will see if this 0 or 1 that you measured from that sentence space qubit matches the labels of the training set. If it matches the labels, you're happy. If it doesn't match, you have to update your parameters of the circuit and send it back to the machine, estimate again the 0 or 1 value, and send it back and see if it's matched now. So you go through this loop until it converges. And this is basically, what I've described is basically a supervised binary classification task for machine learning. But instead of neural networks, as you would do in classical machine learning, we're using quantum circuits. So this is a form of quantum machine learning, as it's called in the quantum machine learning literature. So this is the task that we did. It's we're training the parameters that prepare the meanings of the words so that the binary labels of sentences are reproduced. And then the idea is that you will generate, after you train, you create a new sentence, and then this new sentence can be converted to a circuit, and then maybe this sentence, you know, is a sentence like Chomsky is an anarchist, and then if you measure the qubit with high probability, say 93%, then you know it's an affirmative to this. So that would be testing your training. You're training on your sentences of your training set, and then you give new sentences of the new vocabulary and the same grammar, same vocabulary and same grammar, so that you check or you test basically the parameters that have been learned. You test if it's learned. Can you please review the QML part again? Here, for classifying the sentences, they are treated individually without any contraction. Is it true? I will review the QML part again, and then I will address the other sentence, the other question. So let me review. So we have sentences and labels. This is a training set. We start here, number one. Every sentence individually is mapped to a circuit. So this is a set of circuits. All of this set of circuits is sent to some quantum device, and then measuring the qubit which carries the meaning of the whole sentence. And this qubit can only give you two values, two classical values with some probabilities. So there is a probability to measure 0. There is a probability to measure 1. So this is the probability that the sentence is false. This is the probability that the sentence is true. If it matches, if say this is very high. So if this is, let's say, 0.3 and this is 0.7, but for sentence I, and it happens that the label of the sentence I in the training test is 1, then you're happy. But if it was 0, you're not happy because it mismatches. So you have to send it this checking whether there is a mismatch happens classically on your laptop after you read the results of your quantum computation. What you have to do then is update these thetas, tweak your parameters, you know, change your settings in the circuits so that the states are modified because they're not what they should be. The states that you're preparing are not doing the job of encoding the meaning correctly so that the labels are produced. They don't have the correct meaning. So you update them and you run the circuits again and you check again if the labels are reproduced. If they're not, you update the thetas again. And you do this until you converge. So is this clear? Yeah, I guess it is. Okay, so another question is, for classifying the sentences, they are treated individually without any contraction. I'm not sure what contraction means, but if you're saying tensor network contraction, there is no contraction happening here classically. What's happening here is quantum measurements are happening in this part, and they play the role of the grammar. And yes, they are treated individually because each sentence gives you a different circuit. And that the cost function says that the sum of all of the labels have to, so the sum of the mismatches of all of the labels has to be minimized, for example, with some distance that you like. You can take absolute value, you can take square, you can take relative entropy, whatever you like, some monotone. But yes, every sentence is treated individually in the sense that it gets mapped to its own circuit. Of course, some words will participate in many sentences. So for example, in the corpus, you might have, Chomsky is an anarchist, Chomsky is old, Chomsky is a linguist. So Chomsky appears in all of these sentences. So, because if it wasn't like this, if it was that a word appears only exactly in one sentence, then there wouldn't be enough correlation between the sentences for the training to work. It would be just a meaningless thing. So that's basically what I described here. What we call is some sort of question answering, where you train your thetas and then you generate a new sentence with the same words, same grammar, same vocabulary, same grammar, but new sentence. And then you compute its truth label, and you do this by converting a question to a statement and running its circuit. And here I've written a Medium blog where I'm describing basically what's going on in this talk and also in this question answering task. But you won't find much more detail. It's basically this talk, but in a blog post. And you can find this in a Medium, in this Medium address. There is another question. Has this been tried with languages other than English, say Thai or Turkish or Finnish, which don't behave the way English does? Yes, good question. So I've only seen English, and however, there's been works on pre-groups where there are pre-group grammars for Persian, Irish, French, and I think in general the conjecture is that that most languages are described by pre-groups in the same sense that pre-groups are weakly equivalent to context-free grammars. So pre-group grammars, the grammar model I'm using here is weakly equivalent to Chomsky's context-free grammars. I know that most languages are not fully described by context-free grammars, but I think they are to a high degree. So there are linguistic phenomena where you need context-sensitive grammars, but you know they are as good as context-free grammars. So I think I hope this answers your question. The other question is, are there any approaches in quantum machine learning where the training part, if also performed by the quantum machine, as compared to classical searching the parameter space as it's done here? I'm not sure I understand this question. Where the training part is also performed by the quantum machine. Ah, okay, I see. Yes, there are proposals where you do training in superposition, but it's not clear if you, okay, first of all, it's not practical in NISQ devices. Everything that is done now with NISQ devices and training some parameters to do any task from chemistry to finance to whatever people use quantum machine learning for with parameterized circuits, the training is done classically. Let's say it's long term to be able to train stuff in parallel or to do optimization problems in parallel. People have proposed also training in parallel classical neural networks on a quantum computer where you do, you know, you're searching the space of classical parameters for the weights of a neural network with some Grover algorithm, but this is a bit far into the future. So that's why we did this classically. Because also we wanted to run something on an actual device beyond just you know, sketching algorithms for the long term. However, we are working also for long-term algorithms, but what we did so far was for NISQ devices. Is it possible to obtain the meaning of a type maybe, or a text, maybe there's a typo, by tensor contraction of several sentences? Oh, a text, yes, okay. Yes, so so the idea here is that sentences refer to each other with some anaphoric connections. These anaphoric connections would again correspond to wirings. So in the end, if you have a bunch of sentences that refer to each other with pointer anaphora, where you have to do resolution on them and so on, you would get a bigger circuit through this wiring. So Bob has written a very high-level paper on this called The Mathematics of Text Structure. For anyone interested, they can go and look this up. This is the title, Mathematics of Text Structure, by Bob Coecke. And yeah, basically the idea there is sketched like this. So I hope this answers this question. Let's see. Thank you. Yes, of course. Okay. So this is, yeah, let me get back to phrase similarity, and then I'm going to conclude. So this is what phrase similarity would look like. This is another task. So this would be the n wires, and this would be the s wires of two sentences where I've joined them. So joining two sentences is basically taking an inner product. So as we said before, this is a big vector because it has one leg sticking out. This is another big vector, but upside down or 180 rotated. And basically it's an effect, right? So it's a state coming into an effect, and the whole thing is a scalar. It's a number. So basically, if this thing is a vector psi and this thing is a vector phi, what this whole diagram is representing is this number. So if these sentences, for example, are orthogonal in meaning, this will be very close to 0. If these sentences are synonymous, then this thing would be close to 1, and so on. So for example, kids play ball, we have apes are social. Maybe it will have high overlap. And kids play ball, and here I have computers run code. This will be of lower overlap. I see we have more questions. Quote the link. I think this includes the references to archives papers. Yes. For the classical ML audience here, can you share with us some NLP tasks that the quantum approach outperforms, and how much? Okay, so with quantum machine learning, outperforming is kind of hard to benchmark. It's still in a very early stage because also the devices are very noisy, so it's hard to scale up. But there is a provable speed up for the task I'm talking about right now, which is phrase similarity. We're basically finding the closest vector with, of a, for example, if you want to classify kids play ball, and you want to see if it's close to, so kids play ball. I'm taking this example from the Zeng-Coecke paper. So here, if you put here sports, or if you put politics, or if you put, I don't know, sports, politics, I don't know, fashion. So blah, blah, blah. Each one of those is a vector. If you want to find the closest vector out of a class of finitely many vectors, so like a multitask classification, if you want to find the closest vector, there is a Grover-style algorithm in the Zeng-Coecke paper, which gives you a quadratic speedup. So for example, basically as in any quantum search algorithm, it's an adaptation of that kind of algorithm where you search on an unstructured database and you find the marked element that you want. But this one requires a quantum RAM, it requires efficient preparation of the states, and also it requires fault tolerance, because to be able to run Grover on the machines that we have today is a bit science fiction. So this is the answer to that question. Are there any other questions? Because this was the end of the talk. Why would computers run code have lower phrase similarity to kids play ball than apes are social? The first two are subject, transitive verb, object, while the latter isn't. Oh, I see. So we're not comparing them. We're not comparing the grammar. We're comparing the meaning. So how close they are in the meaning space. So, but don't take that example too literally because I came up with it like 5 minutes before the talk. And also we haven't run the circuits corresponding to exactly those sentences that you are asking about.
Right, but when you say meaning, can you justify, like, just verbally, why do you think apes are social is closer to kids play ball?
Well, because, you know, playing ball is a social activity and kids are apes, for example. It's some sort
Yeah,
of,
okay.
it's some sort of entailment I'm thinking about, you know, like there is a paper, paper by Martha Lewis and Gemma de las Cuevas, for example, which is building on a bunch of entailment research on disco cat, for example,
Yeah.
by Dimitris Kartsaklis and others of the disco cat literature, where the title of the paper is, if I remember correctly, climb, what is it? Cats climb, entails mammals move, for example.
Sure, okay, but in this case, if it said kids play solitaire, solitaire isn't a social activity. Would that should kids play solitaire then should be definitely closer to computers run code than apes are social, right? There's
Hopefully.
no.
Hopefully, I mean, it also depends on the corpus, right? I mean, here the corpus effectively is what we have in our heads from our everyday experience, right? If I'm feeding some fantasy novel in my computer as a corpus where these, you know, ball has a totally different meaning than the whole thing changes.
Est élu à la primaire républicaine américaine. Qui parmi vous aurait pu prédire que c'était lui qui allait gagner cette primaire?
Sorry?
I don't, somebody else, not me. I don't know who that was. But yeah, I mean, just not trying to be pedantic, but let's say kids play ball. We assume it generally connotes that it's social, but they could be playing it themselves individually. They could be playing it on a PlayStation. So
yeah, sure. I mean, this is all context dependent.
Maybe we could add explainability to the roster of the to-do list for quantum NLP. Explainability.
Right. But I'm saying that in itself, this is also a hypothesis. We have two hypotheses: kids play ball on their own, and kids play ball socially. And we just decide based on the whatever knowledge base that kids play ball socially is more likely. But again, if the whole point of this is we can entertain lots of hypotheses, we should entertain the hypothesis that they're playing it on a PlayStation individually at home.
That's right.
Like
that would be the distributional part that comes from basically the context of the corpus that you're training over. So if kids and play appear in many sentences enough time so that the meaning is captured distributionally, then fine, then it would work hopefully. But do you see my more simple example, my simpler example of kids play ball, and okay, let's make it football, and let's think that we're in England and not America,
or soccer, as they say over here.
Yeah, I mean, probably it doesn't matter for this because I have a 3-class classification here for sports, politics, and fashion.
Yeah, sure.
You would agree here that, you know, one of them would be closer than the other two, so sports would be closer.
Sure. But let me take it on. It's almost impossible to play football on your own. But if you say kids play chess, if we said kids play chess with a computer against a computer, then that's not social. It's sports, but it's not social. So you have an implicit subcategory of social team sports, individual sports, and sports that could be either. You know?
Yeah. Yes. Sure. Yeah, I agree. Of course.
This is Seth. In the interest of time, we have a few more questions, and I think that maybe we can keep this on the to-do list. As you said a moment ago, this work is in a fairly early stage.
Yes,
we have a few more questions in the Q&A.
Yeah, I see there is one by Ruby. What is the advantage of using quantum approach over neural networks? Also, can this approach be generalized for non-quantum computers? Okay, what is the advantage? So the advantage that we started from was the same motivation from the Zeng-Coecke paper that I cited before, which was, you know, you're trying to shove a lot of big high dimensional spaces onto fewer, you know, logarithmically fewer number of qubits. So it's the advantage of encoding. But then you have the problem of, you know, loading, efficiently loading and reading your classical data from the quantum state preparations and quantum measurements. So what is the advantage of using quantum approach over neural networks? It really depends at which level the question is asked. I mean, today, you can do, of course, more efficiently things with neural networks instead of quantum computers because we don't have quantum computers that are as scalable yet. There are a lot of results in machine learning that are being, in quantum machine learning, that are being kind of shot down by a bunch of dequantization algorithms, which is basically so for example, this was started by Ewin Tang. And what Ewin did was dequantize a recommendation system, a quantum recommendation system algorithm, and making it classical, retaining kind of the same structure, and that's why they call it quantum inspired. And basically, the quantum algorithm was claiming an exponential speed up over the classical problem of recommending products to users, like Amazon does or Netflix, for example. But then Ewin, what they did was they made a classical version of the algorithm, which defeats the exponential speed up. So then you would say, oh, there is no use for a quantum algorithm. But the polynomial, you know, the polynomial complexity of that thing was to the 24 or something in the input size. So then it becomes impractical. Then again, some things, there are some papers that show that dequantized quantum-inspired algorithms have much better than worst case performance. So still we don't know if it's worth doing quantum versus classical, because it's hard to benchmark, you know, quantum machine learning, again, I repeat, without having scalable, fault tolerant, fully controllable quantum computers with a very easily used, like Python-like quantum programming language. These things are all still like in prototypical stage, which is a bit annoying, but also kind of exciting as well. So I would say there is the advantage of doing things differently, let's say, but a proven advantage in quantum machine learning or any quantum computing task which is doable today, I don't think there is one. But that doesn't mean that we should stop all of quantum research today. So for example, the best claims of advantage are in quantum chemistry, where they use similar techniques that we are using here with parameterized quantum circuits whose parameters you train, and they prepare ground states of molecules. And there the advantage is in the accuracy of the energy of the ground state of the molecule that you're trying to study. So, okay, this is physicsy and has nothing to do with language, but it's an area of quantum machine learning where it's actually, it seems that it's actually worth doing. And basically, this is the set of motivations in a summary of why go quantum with natural language. And also to repeat again what I said before, that language is quantum native, right? Some grammatical models like this one have a compositional structure which really reflects the one of quantum theory. So why not do it? I see another question. Are there any common points between QNLP method and a formal semantics such as lambda calculus? I'm not sure how to answer this. I'm sorry, I'm not sure. I mean, the pre-groups are formal. Let's see. I mean, it depends where you send your pre-groups. So if you send your pre-group types to some logic, or if you're doing or if you're working with a formal grammar, then you're drawing diagrams out of it, where the semantics and the syntax, well, let's say there is a grammar model where all the semantics is in the syntax, then the diagrams that you draw will have a diagrammatic calculus, and then I guess doing diagrammatic manipulations of that would be computing the semantics only by the grammatic operations. This is the only thing I can think of to say to answer this. Have they mapped a dictionary? Not yet, Chris. Not yet. Can you please repeat or type the name of the algorithm? ZX something. Okay, so ZX calculus is a fully diagrammatic language. All of the syntax is diagrammatic. It's for tensor networks over complex numbers, but it was produced for reasoning about the foundations of quantum theory. And now it's used for optimizing quantum circuits. The ticket compiler that I mentioned before by Cambridge Quantum Computing is also using it as in the inner workings of its compiler to decompose the circuits and reason about them. So basically, it's a language that where computation is done by rewrite rules on graphs on which tensor networks are defined, and these tensor networks are similar to what to the ones that I've shown here. They are states, processes, and effects. And anything like that is a tensor network, and ZX is a universal language to reason about them only with graph operations. Okay, I see there are no more questions. I hope I answered as much as I could.
Are there any concluding remarks you wanted to make?
I think we covered everything. Concluding remarks. So
did you want to put your contact information up? I can't remember whether you had that in an earlier slide.
Yeah, this is my email, my CQC email. And concluding remarks about the work is that the DiscoPy GitHub repo is still being developed. We're experimenting with different tasks. We're scaling it up to see when the noise, we're scaling the dimensions up as far as the noise allows us, because we don't have error correction. Error mitigation has to come in. Error mitigation is also being developed as new tricks are coming up all the time. But also we are thinking long term. So we have started the thread of Zeng and Coecke, where basically you assume that you have a fault-tolerant quantum computer. You assume you have a quantum RAM which efficiently prepares states for you, and it would be very interesting to see what these things can do for having a full-blown quantum computer can do for NLP. But what we have done so far in this last year only that we started this thing is QNLP for NISC. And yeah, final remark is basically stay tuned. We have more stuff. And also, we're all physicists except one computer scientist and one mathematician. And so the NLP side is also we're still learning it, most of us. And we come to the NLP from the computer science foundational approach as physicists. So if you have any comments on the NLP side, they would be very helpful. And thank you.